Hi everyone, this is going to be the fourth lesson on the topic of mechanics for GCSE physics students. In this lesson we're going to be taking a look at gravity, gravitational forces, and we're going to look also at the concept of centre of mass. So let's take a look at the learning objectives for this lesson. So once you've watched this lesson video, and if you're watching it on my website on its lessons page, once you've completed the interactive pop-up questions that will pop up throughout the video, and also the interactive quiz and the simulations on that page, you should be able to do the following things. Now there's a lot to get through in this lesson, and some of the concepts that I'm going to be going into in the later part of this lesson are going to be somewhat more advanced and probably go into a little bit more depth than you actually need for a GCSE physics course. But again, as always, my goal here is to give you guys a more solid and deeper understanding of these concepts so that you find GCSE level questions a bit easier and you can make your way through even the most challenging questions with relative ease. Now, to those of you who are joining me live for this lesson, the students in attendance, I realise that many of you have asked a number of questions which I will be getting through in the Q&A segment towards the end of this lesson. But as always, if you're enrolled on this course and you have any questions following this lesson, you can simply go to this lessons page and you can either leave those questions for me in the live chat on that page where other students can get involved and start a discussion, and I will also respond, or you can send me your questions as private messages and I will get back to them roughly within 24 hours. If you're not enrolled on the course and you are watching this on YouTube, for example, feel free to ask me any questions in the comments section and I will get back to you there as quickly as I can as well. So there's a lot to get through in this lesson, so let's get started here. Now, we first need to distinguish between a couple of terms. So I'm going to start with more basic concepts, and then later on we're going to be looking at some more advanced examples. So let's distinguish first of all between mass and weight. So mass is a measure of the amount of matter that an object is made up of. So when we talk about the mass of an object, we're actually measuring the amount of physical stuff that that object is made up of. Now, as we mentioned before, mass is a scalar quantity. It simply has a defined magnitude in kilograms. So your mass, if you're standing on the surface of the Earth, your mass is exactly the same as if you stand on the surface of the Moon, provided, of course, that you haven't added to your mass by eating or detracted from your mass. Your mass will be the same. So the mass of a 1 kilogram object on the surface of the Earth will be still 1 kilogram wherever you take it in the universe. If you don't chop bits off it or add mass to it, the mass remains the same. Now, weight is a word used to describe the gravitational force acting on a mass, let's say on the surface of the Earth, for example. So if you're standing on the surface of the Earth and you're describing your mass, you're simply describing how much physical stuff your body or whatever object you're talking about contains in kilograms. If you're describing the weight of that object, you're describing the amount of force pulling downwards on it due to its presence in the Earth's gravitational field. So, like all forces, weight is measured in newtons. Now, this can be a little bit confusing for newcomers to physics, just because, again, in ordinary everyday language, people tend to use the word weight and then describe their weight in kilograms, for example. But this is a confusion. Weight is a force, and you should always measure any kind of force, including weight, in newtons. So we're going to get onto the concept of the gravitational fields in a moment, but let's just consider the difference between our weight on the Earth versus our weight on the Moon. Now, I've already said that on the surface of the Earth, your mass will be whatever your mass is. So if you're looking at a 1 kilogram object on the surface of the Earth and you move that object to the surface of the Moon, it will still have a mass of 1 kilogram. But the gravitational field strength on the surface of the Moon is roughly 1/6 that on the surface of the Earth. And so while the mass of that object will remain the same when you move it from the Earth to the Moon, its weight will decrease by a factor of 6. So the weight of the object on the Moon has changed in newtons. It's gone down to 1/6 of the value that it was on the Earth, but its mass remains the same. It's still 1 kilogram of mass. So speaking of gravity then, without getting into too much depth about gravity, what do we mean when we talk about the gravitational force? So I'm going to quickly remind you guys that towards the end of the course, when we get into the concept of energy, there is a whole lesson on the topic of gravitational potential energy, where we're going to be going into the concept of gravity and gravitational potential energy in a bit more detail. But for the purposes of what we're talking about here, we need to clearly describe what we mean by gravity. Now, we're not going to be explaining how gravity works because, frankly, nobody really understands that. Nobody really knows what gravity is or how it actually works. There are many competing theories about that. We're simply going to talk about it in terms of what we know about gravity, the predictable behavior of gravitational fields. So, now, most of the attribution for the key work on gravity goes to, of course, Isaac Newton. Isaac Newton defined an equation which describes how objects with masses will attract each other. So fundamentally, gravity is a field effect. So we've talked about fields before. For example, in the first topic on electricity, we started with the idea of electric fields. Now, as I've said to you before, a field is a vector quantity which changes at all points around an object, will change its value, its magnitude, and or its direction at all points around an object. So what do we mean by a gravitational field? Well, a gravitational field is simply a field produced by masses which attract other masses. So without going into too much depth about kind of vector maths or anything else like that, let's just think about the more simple aspects of what we mean by a gravitational field. So, for example, the gravitational field of the Earth, if we imagine this is the Earth, the gravitational field can be like any field diagram represented by lines of force. Now, all gravitational fields are attractive in nature as far as we know. So the Earth will attract objects that are distant to it by means of a force, a non-contact force. So we mentioned early on in this topic that we can broadly categorize forces as being contact forces or non-contact forces. Contact forces occur when one object pushes or pulls on another object, and because of Newton's third law, we know that forces occur in pairs. If one object exerts a force on the other object, the second object exerts an equal and opposite force on the first. But a gravitational field is a vector quantity, like all fields, and it describes the force acting on a neighboring object due to the object causing the field, and in the case of gravity, that force is always attractive. So we draw the lines of force pointing towards the object whose field we are drawing. So in the case of the Earth, all the field lines point towards the Earth. Now, we can see here from this diagram, and again, this is a two-dimensional representation. Obviously, gravitational fields occur in 3 dimensions. So if this is the Earth, what this means is, if we position an object here, for example, it will experience a force in this direction towards the center of the Earth. And as we'll see, it actually operates, the gravitational force operates towards the center of mass of the Earth. However, if we move this object over here, the direction of the gravitational force changes. The gravitational force is now acting in this direction, again towards the center of mass of the Earth, but its direction has changed. If we now move this object from this location here further out to this location here, the amount of force attracting it to the Earth due to the Earth's gravitational field will change. It will be less than it was closer to the Earth, because the further away you get from the Earth, the weaker its gravitational field becomes. So we can see here from these 3 positions that the gravitational field of the Earth is a vector quantity which changes in its magnitude, as it does here, between these 2 positions. Closer to the Earth, we have a greater force. Further away from the Earth, we have a weaker force. And it also changes in its direction, depending on where you position the object in that field. So the Earth is not the only object in the universe with a gravitational field. Of course, we know from an early age that the gravity is the force which holds the objects in the solar system in their orbits around each other, for example. And we're going to be exploring that in later lessons. For example, when we start to talk about astrophysics and cosmology, the orbits of planets and so on and so forth, circular motion, and these things. So the Earth is not the only object with a gravitational field. In fact, all objects with any mass whatsoever have a gravitational field. The gravitational field is an effect which all objects with mass will exert. But the effect is very, very weak, so that only objects with a very, very large mass in human terms exert an appreciable, measurable gravitational field. So we've kind of covered the basics here in terms of what we mean by a gravitational field. Now, Newton was the first to formally describe in mathematics how gravity operates. He said that any two objects, so if we take, let's say, a mass 1, we have an object with a certain mass, which we'll call mass 1, at this position here. And we have another object with another mass. Let's call this mass 2. They can be different masses, they can be the same mass, they can be bigger or smaller than each other, but we have simply two objects with empty space between them. He said that these two objects will attract each other with equal and opposite forces. So let's call this force here the force of mass 2 on mass 1. So this is the force with which mass 2 pulls on mass 1. And you can see that it's pulling on mass 1 with a force towards its own centre of mass. So this is the force of mass 2 on mass 1. But, again, Newton's third law, forces occur in equal and opposite pairs. Mass 1 will attract mass 2 with a force of equal magnitude but in the opposite direction towards its centre of mass. So let's call this force of mass 1 on mass 2. Now, Newton gave a formula which describes the magnitude of these forces in relation to the masses and the distance between their centres of mass. Now, we'll talk about what centre of mass means in a moment. So we have these two objects, and let's just assume they're spherical objects with a centre of mass located in the centre of the sphere. Uniform, homogeneous spherical objects, very simple, with centres of mass located at their centres. So the distance r is the distance between their centres of mass. So this was the formula that Newton gave. We have this vector here, force of mass 2 on mass 1. We have this vector here, force of mass 1 on mass 2. They are equal in magnitude to each other, but opposite in direction. So we can say that the magnitudes of these two forces are equal. Now, when we give the magnitude of a vector, we put bars around it. So we can say that the force, the magnitude of this vector, this force of mass 2 exerted on mass 1 is equal to the magnitude of the vector of the force of mass 1 on mass 2. So the two magnitudes, the size of this force in newtons is equal to the size of this force in newtons. But Newton gave us a way of calculating or relating these masses and the forces between them and the radius. So he said that the force of gravity that is exerted between two masses which are equal to each other is equal to a constant, which we'll call g, we'll talk about that in a moment, multiplied by the product of their masses, mass 1 times mass 2, divided by the square of the distance between their centres of mass. This equation is sometimes referred to as the law of universal gravitation. Now, the reason why it's called this is because it describes all the gravitational forces acting between any two objects anywhere in the universe. Now, if we pause to consider this in a little bit more closely, this is just a constant. We'll talk about this constant here in a moment. So, any two objects will attract each other with a force, with equal and opposite forces, which are proportional to the product of their masses and inversely proportional to the square of the distance between them. Now, in theory at least, these two masses can be any distance apart. So this distance can be as big as you like. And yes, this means that you're dividing by the square of a larger and larger distance as this distance increases between these two objects. But this means that the force between them never actually reaches zero, which means that every object in the universe attracts every other object in the universe, which has mass, with a gravitational force. Those forces, if those objects are very far apart, can be infinitesimally small, but they're never actually zero. So often you will hear physicists refer to the gravitational field, which permeates the whole universe, which is the sum of the gravitational fields, the gravitational interactions between all the objects in the universe. But at a very simple level, this is what Newton said. Any object with mass will attract any other object with mass with equal and opposite forces between them, acting at a distance, and the relationship between the magnitudes of those forces is given by this equation. The gravitational force between the two objects is equal to a constant g multiplied by the products of their masses divided by the square of the distance between their centers of mass. Now, I include this equation even though it doesn't appear in most GCSE physics specifications, simply because it's well within the ability of GCSE physics students to understand, and it actually adds a lot to your understanding of gravity if you understand this equation. Don't feel as though you need to memorize it or learn it. I only include it here for the purposes of what we're going to be discussing, and so that you can get a better understanding here, and also because some of the students who are currently in attendance asked me to talk about it well in advance of this lesson. So this gives us a relationship which allows us to calculate the gravitational forces between any two masses. So it's not just the Earth. Technically, this pen has a gravitational field of its own. It has a mass, and the Earth also has a mass. And so the two objects, the pen and the Earth, attract each other with equal and opposite forces. The pen is attracted towards the Earth with a force that we call the weight of the pen. This is what we mean by weight. It is the force acting on the pen towards the center of mass of the Earth. But the Earth also experiences an equal force in the same magnitude in newtons as the weight of the pen, but acting in the opposite direction. It acts upon the Earth towards the pen. But obviously the Earth is so much more massive than the pen. It has so much more mass that that force, the effect of that force acting on the Earth towards the pen, is negligible and doesn't really affect the motion or the other characteristics of the Earth. However, the force of the pen on the Earth is significant from the point of view of the pen and the human being holding it. So weight, when we talk about the weight of any object, we're actually talking about the force of the Earth on that object. So let's talk a little bit more about the gravitational field strength of the Earth. So I mentioned that this constant g is a constant. We call this the constant of universal gravitation. Universal gravitational constant. So it's one of the fundamental constants of nature. It is simply a number, and again, you don't necessarily need to know this number for GCSE physics courses. I include it here simply so that we can show a few things which will be of interest to you and will give you a better understanding of gravity. So let's take a look at this. Now let's simplify this here a little bit. Let's just talk about the magnitude of either of these forces as being the force of gravity here. So the force of gravity is equal to some constant g multiplied by the product of the two masses, m1 and m2, whatever those masses are, divided by the square of the distance between their centers of mass. Now, the constant g has obviously a specified value. Now, it's been measured to a very high degree of precision. I'm going to kind of round it to 3 decimal places here. It has a value of 6.674 times 10 to the power minus 11. Now, the standard units of the gravitational constant are meters cubed per kilogram per second squared. Now, these are the standard SI units, Système International units. And these are actually based on a slightly more kind of high-level concept of Planck units. Now, Planck units, I'm not going to get into here. They're simply a system of units based upon 5 physical constants which all have a value of 1 when used in these units, and this is why they are the standard units used internationally for the gravitational constant. For us, for our purposes, we're going to use slightly more useful units for our discussion here, by rearranging this equation here to have a look at what the units of G would be if we gave them in terms of the quantities in this equation. So we have force on this side. So we have newtons on the left-hand side, the force of gravity. We have G, which we're going to work out what the units are by rearranging the equation. And we have on the multiplied by G on this side, we have two masses. So kilograms times kilograms gives us kilograms squared. And we have R, a distance whose standard units will be in meters, and it's squared, so we have meters squared. So the units of G are going to be, when we rearrange this equation, we divide both sides, we multiply both sides by meters squared, and we divide both sides by kilograms squared. So the units of G, for the purposes of our discussion, which are not going to be standard units, which are again based on the Planck units. If you want more information about that, then maybe check out the upcoming A-level physics course, or look this up online. It's actually quite interesting, but we're not going to be using these units. Instead, we're going to be using units that we derive by placing the standard units for mass and distance and force into the equation and rearranging for G. So we can see here that the units for G are newtons meters squared divided by kilograms squared. So in order to understand, or in order to get a bit of practice and get a better understanding of the law of universal gravitation and how gravity actually works, I would thoroughly recommend, again, having a look at these two simulations that you can find on the PHET website. So if you just type in PHET and then the word simulations into Google, you'll find this website from the University of Boulder, Colorado, where you'll find a lot of different useful simulations that you can play around with, including this one. Now, this sim comes in a couple of different versions. There is a basics version and there is a more advanced version. So I'm just going to show you the basic one here for the moment. You can check out the more advanced one for yourselves. So in this case, we have two masses, M1 and M2, and we have separated them by a distance of 4 kilometers, and we can see that mass 1 has a mass of 2 billion kilograms. Mass 2 has another mass of 4 billion kilograms, and we can see here that the force on mass 1 exerted by the gravitational field of mass 2 is equal to 33.4 newtons. Now again, these forces come in pairs, and again Newton's law of universal gravitation and Newton's third law dictates that the force of mass 2 pulling on mass 1 is going to be equal in size and opposite in direction to the force of mass 1 pulling on mass 2. So you can see these two forces are equal. Now if I change the distance between them, let me just turn the sound down. So if I change the distance between them, we can see that these forces decrease. If I decrease the force between them, the forces increase. If I change the mass, both forces will increase if I simply just changing mass 1. And this makes sense because if we're changing one of these masses, then the whole top of this, the right-hand side of this equation will increase by that factor. So by increasing just one of the masses, we see that both forces increase in magnitude. If I decrease just one of those masses, both forces decrease in magnitude. So you can play around with this simulation, and these values, you can actually see that they do work out in the equation for universal gravitation from Newton. So this gives you a sense that all objects attract all other objects, and they attract each other in pairs with pairs of forces which are equal and opposite, and the magnitudes of those forces can be given by Newton's law of universal gravitation. However, this has certain consequences, and we can simplify things a little bit to understand why the force of gravity acting on an object near the surface of the Earth is usually given as 9.8 meters per second squared. The gravitational acceleration is given as 9.8 meters per second squared, and the gravitational field strength near the surface of the Earth is given as 9.8 newtons per kilogram. So let's take a look at that now. So most of you know by now that the acceleration due to gravity near the surface of the Earth is usually given as 9.8 meters per second squared. So again, we're going to be talking about acceleration in a later lesson in this topic. But what this means is that objects tend to fall towards the surface of the Earth in such a way that they accelerate, and every second that they fall, they gain 9.8 meters per second of speed. So this is typically used in calculations involving gravitational acceleration, and we assume that it is a constant. Now, as we'll see, that's a bit of a simplification, and again, if you consider what I've already said, that kind of stands to reason. Nearer the surface of the Earth, an object will experience more gravitational force than further away from the surface of the Earth. Now again, think of Newton's second law here. Newton's second law, resultant force is equal to mass times acceleration. So the force equals mass times acceleration. Now, if we're assuming that the acceleration due to gravity is constant, then we're assuming that the force is constant. Now, near the surface of the Earth, for human-sized objects, as we'll see, that is actually a fairly good simplification. But in fact, if we look at the idea of gravity as a whole, nearer the surface of the Earth, the force is greater on that same mass than further away from the surface of the Earth. So clearly, the acceleration due to gravity, if the mass remains the same, is going to be different at different distances from the Earth. But near the surface of the Earth, we say, as an approximation, as a simplification, that the acceleration due to gravity is a constant 9.8 meters per second squared. So, from Newton's second law, we can say that the force on an object near the surface of the Earth that we call weight is equal to its mass multiplied by the gravitational acceleration, or the gravitational field strength, which is given as 9.8 newtons per kilogram. So sometimes people will say, I weigh 50 kilograms, when really what they should say is that their mass is 50 kilograms. Actually, their weight, if we're approximating the g to be 10 meters per second squared, as we often do, their weight would be 500 newtons or thereabouts. So on the Earth, for example, if we're approximating the gravitational field strength to 10 newtons per kilogram, or approximating the gravitational acceleration to 10 meters per second squared, a person of 90 kilogram mass would weigh 900 newtons. In space, where there is no appreciable gravitational field pulling them, their mass would still be 90 kilograms, but their weight would be 0 newtons. On the surface of the Moon, where the gravitational field strength is roughly 1/6 that on Earth, their mass would still be 90 kilograms, but their weight would only be 150 newtons. So when we say that an astronaut is weightless, it doesn't necessarily mean that they have no mass. They haven't ceased to exist. They simply have no force of gravity acting on them. Now, again, that is a simplification. As we said before, all objects will attract all other objects, regardless of distance, with some gravitational force, but that effect is incredibly weak. So let's look at this in a little bit more detail here. So if we think of the gravitational force of an object such as, for example, your own body. So if we imagine that I am standing on the surface of the Earth over here, obviously this is not drawn to scale. I'm standing here, let's call my mass m1. Now, the force of gravity, according to Newton's second law, is going to be my mass, m1, multiplied by the acceleration that I experience due to the force of gravity, my weight acting downwards. So this is going to be g in this case. Now, Newton's law of universal gravitation also gives us an equation that will allow me to calculate the force of gravity, my weight, according to the gravitational constant, and my mass and the Earth's mass, m2, and the distance between my center of mass, which is located somewhere near my belly button, and the surface of the Earth. That's going to be r squared here in the equation. So, since both of these equations contain the term F sub g, the force on me due to gravity, my weight, we can equate the right-hand sides of these two equations. So let's do that. We've got m1 times the acceleration due to gravity, g, is equal to the universal gravitation constant g multiplied by my mass multiplied by the mass of the Earth, m2, divided by the square of the distance between my center of mass and the center of mass of the Earth. So we can see here that my mass m1 appears on both sides of this equation, so we can cancel that out. So let's take a look at this a little bit more closely now. So the acceleration due to gravity near the surface of the Earth is going to be given by these terms here: the mass of the Earth, the distance between the center of mass of my body, my belly button, and the center of mass of the Earth, squared. So if we consider this then, and we want to calculate a value for g, let's imagine now I climb let's say I climb to the top of Mount Everest. Well, in relation to the total distance between my center of mass and the center of the Earth, I will have moved upwards a very, very tiny fraction of that distance between my center of mass and the radius of the Earth. The radius of the Earth is huge compared to however high I climb on the surface of the Earth, or however deep into the oceans I dive. The change in height that I experience is going to be very, very small. It's going to be negligible in comparison to the radius of the Earth. Similarly, my mass is very tiny in comparison to the mass of the Earth. So if we consider the radius of the Earth and the mass of the Earth, then even if I climb to the top of the tallest mountain on Earth, Everest, or I dive to the bottom of the Marianas Trench in the ocean, the change in height, the difference, the change in r, the distance between my center of mass and the center of mass of the Earth, will be negligible compared to the radius of the Earth. So let's now use that principle to calculate the size of g. So again, we need to substitute some values in here. So this is the mass of the Earth. This we know, regardless of what my position is on the surface of the Earth, the top of the tallest mountain to the bottom of the deepest ocean floor, it's going to be negligible. The change is going to be negligible in comparison to the radius of the Earth. So this is the radius of the Earth squared here. Now, these values are actually known. We know what the mass of the Earth is to a reasonably high degree of precision. This is something like 5.974. In standard units, we want it in kilograms, times 10 to the power 24 kilograms. The radius of the Earth, again, it's a very, very large number. It's 6.378 times, and again, we're measuring this in standard units, 10 to the power 6 meters. So we have the mass of the Earth, we have the radius of the Earth. We're going to square this down here. We have a value for the universal gravitation constant here. So actually we have everything that we need to calculate the value of g. When we substitute these values in here and we evaluate, and again I would encourage you guys to do this on a calculator, we find that the value of g, once we evaluate, comes out to 9.795 meters per second squared, or newtons per kilogram. So this is actually very, very close to the value 9.8, which is usually quoted. And again, this makes use of the idea that any change in my position near the surface of the Earth, top of the tallest mountain, bottom of the deepest ocean, is negligible in comparison to this enormous radius of the Earth here. So we can simply use the radius of the Earth here for any practical purpose. Now, obviously, the further away we go, if I go up into orbit, or if I go further out into the solar system, then the change in r becomes significant, and then we can't just simplify by using the radius of the Earth. But for most practical purposes, we can see here that the value that is given for the acceleration due to gravity, g, is the value that's normally given, 9.8, is actually a very close approximation. And so this is why we use the value 9.8. So we've talked a little bit about gravity, and again, we're going to be mentioning these principles of gravitation and gravitational potential energy in a later topic, in the energy topic. Let's now move on to the idea of center of mass. So the idea of centre of gravity, and again, we're going to distinguish between centre of gravity and centre of mass in a while. They are sometimes used interchangeably with justification. Sometimes they need to be distinguished from each other. But the idea of centre of gravity was first introduced actually by the Greek scientist Archimedes. Now, he proved that the turning effect of a force, or the turning force that he referred to as torque, exerted on a lever by a weight placed at any point along its length is the same as if all the weight were placed in a single point. He called this point the centre of gravity because he was referring to the point at which the weight appears to act on that object. Now, the centre of gravity is sometimes referred to as the centre of mass. It's not always the same as the centre of mass, as we'll see in a moment, but sometimes these words are used interchangeably. In fact, they don't quite mean the same thing. But let's start with centre of mass. So the centre of mass is usually defined, at least in GCSE curricula and elsewhere, as something like this: the imaginary point in or near an object where the object's whole mass can be considered to be concentrated. So we're going to look at some examples of this in a moment. So, for example, gymnasts will use centre of mass, the principle of the position of their centre of mass, to help them balance, like this person is doing here. Now, what they're doing is they are positioning their centre of mass over where their base is, where their body is making contact with whatever it is that they're resting on. And so as long as this gymnast's centre of mass, and the human body's centre of mass is usually given as being located somewhere near the belly button. That will change depending on how you position your limbs. But here we can see if this is the centre of mass, then the weight can be considered to be acting at the centre of mass, as we'll see. So in yoga, for example, several positions in yoga will use an understanding of the position of the centre of mass to help the person taking up those positions to balance. So this yoga expert is balanced because her centre of mass is directly above her right foot where she's balancing. So let's start with the centre of mass of basic symmetrical shapes. So as I've said, that the centre of mass is an imaginary point where you can consider the whole mass of an object to be concentrated. Now the idea of centre of mass is used in the law of universal gravitation. So when Newton formulated this law, he considered the force or the R to be the distance between the centres of mass of those objects. Now, if we're talking about an object which is a sphere made of a homogeneous material, meaning that it has the same mass density all the way through it, its centre of mass will be located at the geometric centre of that sphere. So, if we're talking about symmetrical, homogeneous objects, objects made up of the same material all the way throughout, with the same density all the way through, then we can find the centre of mass of these objects in a couple of different ways. So let's look at some practical methods first, and then we'll look at some geometric methods a little bit later on. So if we take any symmetrical object, so a square, a rectangle, a circle, or a triangle, as long as they're symmetrical, we can simply hang them by one corner and let them pivot around that hanging point until they stop moving, and then draw a vertical line through the corner and then do that again. So if we do this with a square, we would draw a line down through so we first position the square hanging it by this corner, and as we saw, we drop a plumb line down and draw along it. We do the same thing with another corner. Where those two lines cross is where we find the centre of mass. We can do the same thing with a rectangle. We hang it by one corner and then another and draw a vertical line downwards each time. Where those cross is where the centre of mass is. With a circle, we can do the same thing, although geometrically it will simply be in the centre of that circle. Now you see that in both of these cases, the centre of mass is located in the geometric centre of the object. So we don't even need to do this. We can simply draw diagonal lines between the opposite corners of this square and find the position of the centre of mass geometrically. We can also consider the centre of mass to be the geometric centre for this rectangle or for a circle. And again, if we take a triangle, as long as it's an equilateral triangle, we can consider the center of mass to be the geometric center of that object. So we can do this by means of geometry, or we can do this by a practical method, hanging them by their corners and then drawing these vertical lines down through from where they're being hung downwards and finding where they cross. So the center of mass of an object it can be defined in simplistic terms as the imaginary point in an object, or as we'll see, near an object, where all of the mass of that object can be considered to be concentrated. Now, there's a couple of consequences to this for our understanding of physics. First of all, we can say that the center of mass of an object is obviously, as I've said already, where all of the mass of that object can be considered to be concentrated, but we can also give the center of mass of an entire system of objects by the same definition. So we can say that for a system of objects, not just one, but as many objects as we choose to consider in a system of objects, center of mass is firstly where the total mass of all objects in that system is or can be considered to be located. But again, think of Newton's second law. If the resultant force acting on an object acts on the mass of that object, then if we're considering the total force, the net force on a system of objects, the resultant force, we can also consider the center of mass to be where the net force on the whole system is acting. So, for a system of objects, the center of mass is also where the net force, the resultant force on the system can be considered to act. And this actually makes our understanding of or our ability to do calculations about forces applied to whole systems considerably easier. So for a system of objects, not just one object, the center of mass is where the total mass of all objects in the system can be considered to be located, and because of that, it's also where the resultant force, the total net force on that system as a vector, can be considered to be acting on that point of the center of mass. So, at a very basic level, we can determine the centers of mass of regular shaped objects by this practical method or simply by geometry. But in more complex non-symmetrical systems, without resorting to more kind of advanced mathematics, differentiation and integration in particular, which is, for most of you who aren't studying further maths at GCSE, not something that you're familiar with, we can simply use the same practical method to determine where the center of mass of a non-symmetrical or irregular shaped body is located. So if we imagine we have an irregularly shaped piece of card like this, we can simply, to find its center of mass, we hang it by one of its corners. We then hang a plumb line, which is basically just a piece of string with a weight at the end of it, from the same corner, like this. We then draw a vertical line along that plumb line, and then we hang it from another corner. And we do the same thing again. Exactly the same method as we saw on the symmetrical object, but this is far more useful with a non-symmetrical object. So here we know where the center of mass is, and this is the practical method. Now for GCSE physics, this is pretty much all you need to know. You're not going to be expected to calculate the centers of mass for complex bodies geometrically or by using calculus or anything like that. You simply need to know a practical method for determining the centers of mass of irregular shaped bodies. So let's take a look now at a slight extension of this principle here, because again, I want you guys to understand this at a deeper level. Now, feel free to skip past this if you don't want to go further than you need to, but if you're really aiming for those top grades and to make your life a lot easier, it's a good idea to try and understand things at a deeper level here. So let's take a look at center of mass in a little bit more depth here. So I'm going to need a bit more space. Let me just open up a new document here. And this is also to answer the questions that many of you who are in attendance with me right now have been asking prior to this lesson. So if we're considering a system of objects and we want to understand its center of mass, how do we go about that? Well, actually, there is a formula that we can use to determine the position of the center of mass of a system of objects. So let's start with a very basic system here and we'll build up from there. So let's imagine we have two objects here. Let's say we have two masses. We have mass 1 with its center of mass here, and we have another mass 2, let's say over here. Now, these two masses are some distance, their centers of mass are some distance apart. Let's call this R. They're some distance apart. Now, if these two masses are equal to each other, just intuitively, just by looking at this situation, we would know that the center of mass of this entire system is going to be midway between these two objects. So in this case, if M1 is equal to M2, the center of mass will be somewhere over here, about half R, 1 over 2R, from this left-hand side, or 1 over 2R from the right-hand side. So this is fairly intuitive, but what happens if one of these masses is much larger than the other? Let's say M1 is much larger than the other. So I'm representing it as a larger circle. Doesn't necessarily have to be, it can simply be denser. But let's just say M1 is much larger than M2, and they're still the same, their centers of mass are still the same distance apart that they were before. Well, again, intuitively, we would think that the center of mass of the system has now moved closer to the larger mass. It's going to be somewhere over here, but it's not quite so easy. Without knowing how much larger M1 is than M2, it's not as easy for us to immediately and intuitively say exactly where the center of mass of the system is now. So it turns out that there's a very straightforward way of doing this. So for this system here, we, as always, with any physical system that we're defining, we need to define our coordinate system so that we can define the position of one object relative to each other. Now, in physics, frames of reference and coordinate systems are very, very important, even though for some reason they don't appear in GCSE curricula. So nature doesn't come with its own built-in coordinate system. We, as physicists, need to determine for the system that we're considering how we describe and define the position of one object relative to another. So since this is the larger of the two masses, let's just call this position here position 0, and any distance from that going from left to right along this axis between these two, let's call that some distance, some displacement x. So at this position here, x is equal to 0, and at some distance away, whatever the displacement is, we'll define that in terms of a displacement vector x. So we're just talking about a one-dimensional problem here, just along this axis between the two centers of mass. So this position here is position 0, and this position over here is going to be position x2 for object 2. So x1 is 0 here, x2 is wherever the position of object 2 is. So if we're trying to work out the position of the center of mass, so let's call this x center of mass. We know it's somewhere nearer object with mass 1. So we know it's somewhere over here, center of mass, x center of mass. This is the position of the center of mass relative to this position, which we'll call x equals 0. It's at some distance from here, but we want to actually be able to calculate it. Well, we can calculate the position x of the center of mass by doing a weighted average of the mass times the positions of each of these. So for a system with two objects in it, with mass 1 and mass 2, the center of mass, the position of the center of mass relative to our position 0 is given by this equation. Mass 1 times position of mass 1 plus mass 2 times position of mass 2 divided by the sum of the masses, mass 1 plus mass 2. It's basically a weighted average. So if we consider this two-body system, well, in this case, we have this distance r, we have mass 1, we have mass 2, and we have a distance r between them. So if we know what mass 1 is, and we know what mass 2 is, sorry, this should be x2, beg your pardon, x2 here. So if we know the mass of object 1 and we know the mass of object 2 and we know the distance between them, because m2, x2, where position m2 is simply going to be this distance r. So let's give ourselves some numbers. Let's imagine a situation where we have an object with a specific large mass and another object with a specific smaller mass here. So let's say that this mass over here is 5 kilograms. So we have a 5 kilogram mass here, and we have, let's say, a mass of 1 kilogram over here. We want to find the position of the center of mass of this system, and let's just say we know that their centers of mass are, let's just say, 10 meters apart. So what is the position of the center of mass? Well, intuitively, we know it's closer to the 5 kilogram mass. It's going to be somewhere over here. Let's say this is the position of the center of mass. And we need to define our coordinate system. So since this is the larger of the two bodies, let's just say that this position here on our x-axis here, our horizontal axis, this is at position x equals 0. And we know that this, according to this, if this is our 0 on our x-axis, then this second mass of 1 kilogram, its x is going to be 10 meters. Its position x, relative to this position where the center of mass of this object is going to be 10 meters away. So we have the mass of this object and its position. We have the mass of this object and its position. Where is the center of mass going to be? How far away from the center of mass of this object will be the center of mass of the whole system? So I'm going to pause here and let the students in attendance have a go at this question. Where is going to be the position of this center of mass relative to this position here where we've designated it x equals 0? Okay, so let's go through how we would solve this. So we've designated that this position where the center of mass of this larger object is as being position 0, x equals 0. So we have an axis that we're measuring positions of these objects on that goes from left to right, and the position of this one is 0. So if we were trying to find the position of the center of mass along this axis, the distance between here and the center of mass, we would need to substitute some values into this equation. So let's go ahead and do that now. Okay, so x, the position of the center of mass, is going to be equal to mass 1, which is 5 kilograms, times position 1. Now we designated the position of the center of mass of this object as being at 0 on this x-axis that we defined earlier. So this is going to be 5 times 0. And then we add this to mass 2, which is 1 kilogram, times position 2. Now position 2 is 10 meters away from the point which we designated as position equals 0. So this is going to be 1 times 10, and we divide this by the sum of the two masses, 5 plus 6. So the position of the center of mass in meters, this is going to come to 0, so it's going to be 5 plus 1, which is equal to 6, beg your pardon. So 5 plus 1, which is equal to 6. So this is going to be 10 over 6. In meters from this position, which of course simplifies to 5 over 3 meters. So the position of the center of mass of this whole system is going to be 5 over 3 meters away from the position of the center of mass of this larger object. Now we could have defined the position, our coordinates, such that this position was 0, and we would simply have gotten the position of the centre of mass as this distance here. But you see how this works. It's actually relatively straightforward. Now I'm going to do one more example here of how we can use this equation in situations that you might have come across before. So imagine we have a situation where we have, let's say, a seesaw. So we have a seesaw and we have a person sitting over this end, which is applying a force. Their weight is, let's just say, 500 newtons. And another person is applying a weight at this end of 700 newtons. And the fulcrum here, the pivot point, is in the middle of the seesaw. And let's say, actually, let me make this a little bit more interesting. So let's say the fulcrum, the pivot point, is somewhere over here. And let's just say that we have an object which is made of a material such that the mass of this object, the mass of this whole seesaw, the plank of the seesaw, is, let's say, 60 kilograms. And let's say that the length of the seesaw is, let's just say it's 10 meters. Now, here's the question. Where would I, if we have the fulcrum here at, let's make this 1500 newtons. Let's say that the fulcrum is at a distance of, let's say 4 meters here, let's say 3 meters. I'm not drawing this to scale. So this is where the pivot point is. Now, given what we've already talked about centers of mass, and let's assume that this plank is a homogeneous, symmetrical body. It has a mass of 60 kilograms. Let's say that the gravitational field strength is 9.8 newtons per kilogram, or meters per second squared, newtons per kilogram, or meters per second squared. So what would be the resultant moment on this object? Would it rotate clockwise? Would it rotate anti-clockwise? And what would be the resultant moment when you take into account the anti-clockwise turning effect and the clockwise turning effect? What would be the resultant moment on the seesaw in this situation? So again, I'm going to pause here and let the students in attendance have a go at this question. I may need to open up another document here, but I'm going to pause here and let you guys have a go at this. What would be the resultant moment on this object? Oh, I've forgotten to do. Give you the distances. So let's assume that this 1500 newtons is acting at a distance from. Let's say this is acting at a distance of 2.5 meters. So this is where the 1500 newtons force is acting from the pivot point. And let's say the 700 newton force over this side is acting at a distance of, let's just say that that one is acting at a distance of 6 meters from the pivot point. So now that I've given you enough information, have a go at this, guys. So see if you can come up with a solution to this. What would be the resultant moment on the seesaw in this situation? Okay, so let's work through this. Got a range of answers, most of them correct, some of them incorrect. So what we need to consider here is the weight of the seesaw itself, the weight of the plank of the seesaw itself, because the fulcrum here, the pivot point, is not in the center of the seesaw. It is considerably over to the left-hand side here. So let's have a look at this problem and let's see how we would solve this problem here. So let's calculate, first of all, the anti-clockwise and the clockwise moments, but we need to, as I say, consider the weight of the seesaw. Now, the weight of the seesaw is going to act from the center of the seesaw. So if the seesaw is 10 meters in length, it's going to act 5 meters from the edge of the seesaw. So this is the weight of the seesaw acting here. We know that the weight here is going to be the mass of the seesaw, 60 kilograms, acting from the center of mass of the seesaw, multiplied by 9.8. So the weight is equal to m times g, which is 60 kilograms times 9.8. So if we bring up a calculator here and work out what that comes to, I'll bring it up on screen here so you guys can see. So we have 60 kilograms times 9.8. This gives us 588 newtons. So we have 588 newtons of force acting at a distance of 5 meters from the edge. Now what this means is that this force here is acting at a distance of 5 minus 3 meters from the fulcrum. The turning effect, remember, the moment of a force is equal to the perpendicular force acting multiplied by the perpendicular distance of the force from the pivot point. So what we need is this distance here. This distance here is going to be 5 meters, because the center of mass is 5 meters from either edge, minus the 3 meters of the distance of the pivot point from this edge here. So this distance here is going to be 5 minus 3, which is 2 meters. Also, we need this position here. This is going to be 5 meters. Now, because the weight of the seesaw itself is acting to the right of the pivot point, it's going to contribute to the clockwise moment, not to the anti-clockwise moment. Now, I did this because many of you in your working showed that you had done this, and you kind of it's useful to do this, obviously, because it shows that you're thinking about the problem correctly. But in fact, you only need this distance here when considering this force. So this force of the weight of the seesaw itself is only contributing to the anti-clockwise moment. So now that we've got all of the forces which are acting, we have this force, we have this force, we have the weight of the seesaw itself, we now need to look at the resultant moment. What happens when we look at the anti-clockwise moment and the clockwise moment? Well, we have 588 newtons acting at a distance of 2 meters from the fulcrum here, and we have a 700 Newton force acting at a distance of 6 meters from the fulcrum here. So let's start with the anti-clockwise moment. So the anti-clockwise moment here is going to be the sum of the moments of these two forces. It's going to be this 700 Newton force acting at a distance of 6 meters from the fulcrum. So we have 700 times 6. And the other part of the anti-clockwise moment will be the weight of the seesaw itself acting at 2 meters from the fulcrum. So we have, add this to 588 newtons times the distance of this force, mg, the weight of the seesaw itself, from the pivot point, 2 meters. So this is going to be the total anti-clockwise moment. So let's work this out here. We have 700 times 6, which gives us 4,200. 4,200 plus 588 times 2, which is 1,176. So that's going to give us 5,376 Newton meters. So this is the anti-clockwise moment. 5,376 Newton meters acting anti-clockwise about this pivot point. So let's have a look at the clockwise moment now. Well, the clockwise moment is only the turning effect of the only force that operates to the left of the pivot point. So the anti-clockwise, the clockwise moment is simply 1,500 newtons times 2.5 meters. So this is going to be 3,750. Newton meters. So of the two moments, the anti-clockwise moment and the clockwise moment, the anti-clockwise moment is greater, and so the net moment is going to be anti-clockwise. This object is going to turn anti-clockwise about this pivot point, but we want to calculate the magnitude of that turning effect. So the net turning effect is going to be the larger of the two moments, the anti-clockwise moment minus the clockwise moment. So this is going to be 5,376 Newton meters minus 3,750 Newton meters. 5,376 minus 3,750. So this is going to be 1,626 Newton meters. So this is another application of the idea of center of mass. Now we could just as easily have solved this problem by considering, well, we could have done it a couple of other ways, but this is something that you will see in some moments problems where in the question they will also get you to consider the object on which the forces are acting about the pivot. Sometimes they'll get you to consider this to be massless. Sometimes they'll position the center of the pivot point directly under the center of mass. Now, if this pivot point was directly under the center of mass of this seesaw, then obviously the mass of the seesaw would not contribute to the clockwise or the anti-clockwise moments, and so you could disregard the mass of the seesaw. Since the pivot of this seesaw is shifted away from where underneath where the center of mass of the seesaw is, the weight of the seesaw itself actually contributes to the overall turning effect of on this object. So let's now go on to consider the effect of the position of the center of mass on the stability of objects. So what are the factors affecting the stability of an object? Well, we already saw that we can suspend a piece of card from a point, and once you do that, eventually it will stop moving. It will wobble for a while and it will stop moving. In the rest position, it's said to be in equilibrium. And so objects in equilibrium have balanced forces on them. There is no resultant force, and there is no change in their motion or their position relative to the observer, unless, of course, they're moving with a constant velocity away or towards the observer. So at equilibrium, the moments acting on this card are balanced. We consider the total force, the net force acting on this, to be acting from the center of mass. If that wasn't the case, if it was acting on this corner, the object would rotate around the center of mass. So in this position, there's no turning effect around the pivot point, and this is when the center of mass is vertically below the pivot point. So we can use this as a principle through which we can understand the factors affecting the stability of other objects. So let's imagine we have an object which is stable. So this is one of these kind of clown toys. If we push this object on either side, it will wobble. Now this is because the center of mass has moved when we push it. When we push the object to the right, the center of mass moves so that it is no longer above the point where this object is resting on the ground. So at the moment, the center of mass, let's just say it's here, is located directly above where the object is resting on the ground. It is in equilibrium. If we push it though, that center of mass moves, and so the weight has a turning effect because it is now no longer above where it's positioned. But the object, because it's curved, it will eventually wobble backwards and forwards as its center of mass moves until it returns to the resting position. Now, if we consider an unstable object like a pencil, at the moment that object is stable because its center of mass, somewhere over here, is located directly above where the object is resting on the table. So there is no turning effect of that force. But if we now poke this pencil, its center of mass will move. So when the pencil was poked, it began to tip over to the point where its center of mass was located here. So the gravitational force pulling it downwards was acting around this pivot point and had a moment, a turning effect. Now, as that object tipped further over, there was a greater and greater turning effect around this pivot point to the point where it would fall completely over onto its side. If we have an object like this, though, its center of mass, if we poke it, its center of mass still remains over the position where it's resting on the surface. So we would consider this to have neutral equilibrium. So we have a stable equilibrium here. We have an unstable equilibrium here under these conditions, and we have a neutral equilibrium here. Now again, I'm simplifying somewhat. We can talk about metastable equilibria and various other things, but this is kind of enough detail about the idea of equilibrium for GCSE level anyway. So, for example, these stones have been placed in an unstable equilibrium. If you were to push on these, the whole pile would probably fall over. Now, you might want to consider whether or not these arrangement of stones are actually possible or not. I willingly accept any answers here. That we'll discuss those in the Q&A segment afterwards, those of you in attendance, if you can. So think about whether you think, are these stacks of stones actually possible based upon what we've already talked about? If so, how is it possible? If you think that they're not possible, then, why are they not possible? Type your answers into the Q&A box and I'll address those in the discussion that follows. Those of you watching this as a recording, by all means, maybe start a discussion in the live chat on this lessons page if you're enrolled on this course. If you're on YouTube, give your opinions. I'd be interested to know what you guys think. So, instinctively, from a very early age, we have an understanding of this at an instinctive level. Children will play with piles of bricks and they'll know that they will topple over if you position them in a certain way, and they won't topple over if you position them in a different way. Now, the pile of bricks will actually topple over if the center of mass of the system is outside the base of the pile of bricks. And humans base their sense of balance on instinct, essentially, on it's actually based upon the canals in the ears and the sensors there, but we have an instinctive sense of balance which is actually very acute, and we make use of this in positioning our bodies so that we balance. Now, for example, one of the secrets of a good headstand is to keep the feet and the legs in line with the position between where the head rests and where the elbows are. So as long as your center of mass of your body remains within this triangle, above this triangle, then your headstand will remain stable. So gymnasts will use center of balance to help them balance, as we said before. And so when the gymnast's center of balance is directly above where their feet are if they're standing up, or where their hands are if they're upside down, then they won't topple over. So if we're considering an object resting on a surface, so let's imagine we have this brick. If we were to determine the position of the center of mass of this brick, because it's a homogeneous object made of material which is the same density all the way through, we know that its position is in the geometric center of this object. So if we now increase the angle here, and then check to see if we were to hold this brick like this and then release it, we know it would fall back. Now, the reason for that is that it goes back to what we said before. The center of mass of an object or of a system is where all the forces, the resultant force, can be considered to be acting. So the weight of this object can be considered to be acting at the center of mass, which is again the position where all the mass of the object can be considered to be concentrated. So if all of the mass of the object can be considered to be concentrated at this point, this is where the weight of the object is acting. And so if I position the object like this, where the weight acting downwards is above the base of the object, then the turning effect about this pivot point, so there'll be a component of this force acting in the vertical, acting at this perpendicular distance about this pivot point, this will create an anti-clockwise moment around this pivot point, which will return this object back to equilibrium. So if I change this angle to this side now, so if I change this angle so that now the center of mass is beyond the base of this object, we see that actually it now falls over. Now the reason for that is because, again going back to here, is because now the weight acting downwards here is acting such that this object has a clockwise turning effect, a clockwise moment around this pivot point. And so under those circumstances, it will fall over. But it is possible, at least in theory, to position the object in such a way that the center of mass is directly above this corner. Now let's assume that there's no gusts of wind or even tiny movements of air around this, and that you've positioned this exactly right. Well, in theory at least, it should balance, because now there is no clockwise turning effect around this pivot point, there is no anti-clockwise turning effect around this pivot point. This object should balance. So this is a very famous structure here, the Leaning Tower of Pisa. Now, even though it is leaning at quite an appreciable angle, it has actually remained completely stable for over 800 years. Now, why is the tower not toppled over? Well, the reason is, again, because the tower's center of mass is still located above its base. So there is no, in this case, there is no anti-clockwise moment acting around this pivot point that would cause this to topple over. So this is the reason why, despite the fact that it does lean to some appreciable degree, the Leaning Tower of Pisa has not fallen over, at least not yet. So let's imagine we've got these three boxes of matches here on this table. Now, here's a question for you. If this table that you're looking at here in this diagram was to tilt towards you like this, which of these three matchboxes would topple first? So I'm going to pause here and let you guys answer this question. If you're watching this on my website, the video will pause and you can enter your answer here. Which of these three matchboxes will topple first? Will it be the one on the left, the one on the middle, or the one on the right? Assuming that this table now bends towards you, it's kind of lifted towards you. Seems to be unanimous. Okay, so let's actually watch a video of this in action here. So the reason why it was the one on the right which toppled first is because its center of mass was higher. So by moving this, the matches higher up here, the center of mass of this object is up here, whereas the center of mass of this object is slightly lower, the center of mass of this object is lower still. And so as the table tipped forward, the turning effect around this pivot point on this object became larger, and eventually the weight acted outside of the base of this object before the same thing happened to this object or to this object here. So the stability of an object then is affected by two main factors: the height of the center of mass, and the lower the center of mass, the higher the stability, and also the size of the base. The larger the base of the object is, the greater the stability of the object would be. So double-decker buses, as you see here, these are actually designed to be very stable, so that even if the top floor is filled with passengers and the bottom floor has no passengers, it's still very safe going around corners. It might lean a little bit, but it's not going to fall over. So the old style London bus, the old style ones, would actually topple over if they reached an angle of 40 degrees. At 40 degrees, the center of mass of the object, which is actually located somewhere here, because most of the metallic parts of the bus, the engine, the transmission, and so on, were further down, whereas the top of the bus is made from relatively lighter materials and there's less metal in it. So most of the mass of the object is concentrated down here. Now, what this means is that this object will topple over once the angle reaches 40 degrees, because now, if it goes beyond 40 degrees, the weight will be acting down on the center of mass, and that weight will be acting outside of the base of the object. So at 40 degrees, the center of mass moves, anything further than 40 degrees, the center of mass moves outside the wheelbase, and so the bus would start to topple over. Now, a newer, more stable design of bus is now common in the UK. So, in this newer design, the wheelbase has been increased, the width has been increased, and also the center of mass has been moved lower down, so that now you can lean this object to a much greater angle before you start to see the object fall over. So this is an application of the center of mass. This illustrates to you that the stability of an object is based upon two factors. Which two factors is the stability of an object based upon? Well, again, as we saw before, it's based upon the position of the center of mass, the height of the center of mass above the base, and also the width of the base of the object, in this case the distance between the edges of the two wheels. So the stability of the bus has been increased by making the center of mass lower, by decreasing the height of the center of mass above the base, and by giving the new design a wider wheelbase. So here's something for you guys to consider, and again, those of you in attendance, you might consider this, and we'll discuss this in the discussion shortly. How would increasing the number of passengers on the top deck of the bus affect the stability of this bus, even this new design? So to finish off, I'm going to show you this photograph. This is actually a photograph of a van that was involved in a real accident. Luckily, the passengers were fine, but the van ended up at this incredibly precarious angle. It's actually balancing on these two wheels, and it's balancing. It's not falling over to this side or falling over to the left. So why was it unsafe to leave this vehicle in this position? And would it need much force to turn onto its side here? Okay guys, so that's going to do it for this lesson. I hope that was useful to you. I'm now going to go into the discussion with the students in attendance. I realise that many of you in attendance have asked me to go into some more complex examples. I'll do that now, but for the purposes of those of you watching as a recording, if you have any further questions, as I say, if you're watching this on YouTube, type those into the comments. If you're watching this on my website, you can either leave those as private messages on the lessons page when you're logged in, and I'll get back to you within 24 hours, or you can type those in the live chat on this lessons page, and I'll get back to you there as well. Okay, everyone, thanks for watching. I'll see you in the next one. Take care.